In this video, I would like to walk through a biomedical software project that I have completed in the past. So the background is that we are investigating treatment mechanisms for peripheral arterial disease, also known as PAD. And usually this is talking about the artery that goes through our thigh. So imagine this circle as a cross section of the artery, and this shadowy part is the plaque buildup inside one's artery. And we traditionally would use a wire. So imagine a wire to puncture through this lesion or plaque buildup. However, it has been proven to be not very effective, relying on the physical puncture force alone generated in a rather mechanical fashion. So a novel treatment was to again insert a wire, but also now you connect electric current to it, so it essentially burns through the the plaque. And that was basically the purpose of our investigation. We want concrete numbers to prove that ablation is more effective versus no ablation. In terms of the experiment setup, again, this is quite a unique project. Most software engineers don't really tinker with the more mechanical setups or the kind of basic science aspects of experiments. So in terms of setup, we 3D printed some tiny discs about 1 inch in diameter. And like I said, it's a disc, so it has a divot in the middle. What we did was we had a tiny piece of, believe it or not, we had a tiny piece of pepperoni or chicken breast to simulate artery lesion, because those samples are obviously hard to get, highly regulated. And this will also be submerged in a saline bath. And this represents waves. And from that point on, we tried to run a wire, the ablation wire, and the more traditional wires without any ablation. We also had other mechanical gadgets that measures the puncture force. So right here, this device, let me use a different color, yeah. This orange device, which measures the puncture force. And from that point on, as we collect the data, uh, we need to interpret it, right? So it is actually a time series data. So when we plot this, it looks something like this. This is the time axis, and this is the puncture force. And sorry, I'm having technical difficulty with illustration. I want to have a more precise plot that I can show you. So while we are waiting on this, a little fun fact. I actually visited the company that produces this ablation wire, as well as like it obviously connects to a machine, right? It doesn't just generate electricity on its own. So I'm going to put this diamond shape to represent the machine. So when I worked on this project, I visited the company that produced the wire as well as the machine here in Canada. I believe their manufacturing is also in-house. I even shook hands with the CEO. The company's name is Bayless. I swear I didn't know he was CEO, but it was pretty cool, even though I found out afterwards. Okay. So usually if you plot the data collected by the mechanical device, it looks something like this. So as the wire advances, it starts from 0, and then there's a lot of small deviations as it's trying to puncture the lesion. And in this case, we are using our own material to simulate a lesion, and then when it actually punctures, it goes something like this, and pretty much goes down to 0, and it stops. Our goal is to essentially smooth out the curve to find out this point, which is where the true puncture force of this treatment. And to accomplish, essentially we want to accomplish something like this. Let me plot another diagram to illustrate. Actually, let's overlay these two, because I think that gives us a better comparison. Essentially, we want... Wait. Essentially, we want to preserve the bigger deviations, and we want to eliminate the smaller noises in this curve or in this line plot. And I think the beginning is probably where it's the most applicable, because it's very obvious that this will start to decline as we uh, as it has been punctured. So this is where the software part comes in. It's uh, what I did was I implemented something called the Douglas Puchter algorithm. So yes, so this is exactly what it does. It's a line simplification algorithm to reduce the number of points in a curve while preserving its overall shape. The result is that I analyzed um, a lot of pepperoni pieces and chicken breast pieces, and the conclusion is that ablation provides a significant boost in terms of the puncture force, and that proves our hypothesis. For me, from this experience, the most valuable learning is collaboration with a very cross-functional team. And in the context of software, usually you think about, okay, I need to collaborate with sales, I need to collaborate with um, QA or solutions, go-to-market teams. But in this case, for me, it's a very, very clinical team. I was working with a surgical resident who also pursues a PhD. Like, she was one of the MD plus PhD kind of doctor. And also the biomedical and mechanical engineers from Baylis, as well as a master's student who worked on a precursor of this project. She looked a lot more into the peripheral arterial disease itself. I did a lot of the experiment setup, and it's quite a different experience when you cannot fully simulate something using software alone. Like the data collection, we couldn't just, unlike the best example I can think of would be online advertising, or for machine learning, we can easily find data online. This had to be hand collected. Uh, I learned to work with the ablation devices, the mechanical device where the puncture force gets measured, uh, and making up the saline solution, as well as uh, well, for me, it's pepperoni and chicken breast. I did not work with human samples. And something I did for this project, I also, let me just upload this. So, as part of the project, I participated in uh, open house event with grade school children who are interested in medical sciences. It's definitely a project that's very unique. And my only regret is that this algorithm, at the insistence of a more clinical facing um, working group, they strongly preferred using MATLAB as the programming language to perform this type of data analysis. However, as we all probably know, MATLAB is not really designed for software engineering. I doubt that the code was written in a way that can be maintained over time. And I feel like, as someone on the team who was clearly more software engineering oriented, I should have tried my best to contribute, uh, and also like basically convincing everybody that we should go with Python instead. It's also much easier to to use, because for MATLAB we had to apply for a license, and that's my only regret as a software engineer on this project. Overall, feel like it's a very meaningful project where I got to contribute to meaningful research, and I'm glad you found this video. If you find it helpful or not helpful, leave me a comment down below, and thanks for watching.